The headline from Bloomberg says, Apple is readying new iPad Pros and a redesigned MacBook Pro for 2027. But if you are building AI applications today, this news signals something far more dangerous than just faster chips. It warns that your current local machine learning stack could become fundamentally broken by the time these devices arrive. The issue isn't raw speed or flops numbers anymore. It is a collision between legacy software design and a new hardware reality, where the neural engine becomes the primary compute unit for inference, not an afterthought. If you architect pipelines expecting generic GPU acceleration or CPU fallbacks, your systems will face latency spikes and power inefficiencies that render them unusable in real-world scenarios. This shift forces us to rethink how we move data across our devices before battery life dies from inefficient computation. To understand why this matters for your career as an engineer, we have to look at the transition happening under the hood of modern silicon. For years, developer intuition has relied on a simple rule: more floating point operations per second equals better performance. We assumed that if we threw enough GPU horsepower at a problem, it would get solved faster. But research into what is emerging as the GenAI paradigm indicates this assumption is no longer valid for generative tasks. The shift from retrieval-based processing to generation and synthesis requires massive parallelism in ways that general-purpose cores simply cannot handle efficiently. In 2025, leading supercomputers are already running on clusters of over 200,000 specialized chips because the power-to-performance ratio required for these generative tasks has outgrown what standard CPUs can provide. This same constraint is now squeezing down onto consumer devices like iPads and MacBooks. The engineering reality is that future inference will rely heavily on dedicated accelerators rather than general-purpose cores. When a developer continues to route heavy tensor operations through standard GPU drivers or CPU fallbacks without leveraging specific optimizations for the neural engine, they are fighting against the architecture itself. The data has to move from memory to the processor and back again in ways that create bottlenecks. In current stacks, data often flows from the central processing unit to a graphics card and then returns. Future Apple architectures prioritize the neural engine as the primary inference engine for generative tasks. If your code does not speak this new language efficiently by minimizing data movement between RAM and these dedicated tensor cores, you will hit a brittle ceiling where latency exceeds user tolerance and battery drain becomes prohibitive. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Consider how different hardware handles the workload of generating text or images compared to searching through documents. We are moving from a library search engine model that CPUs excel at toward a creative writer's desk scenario that demands specialized parallel processing. This is not just about speed, it is about data locality and architectural fit. If an ML pipeline is architected to route heavy tensor operations through general-purpose cores without leveraging specific metal performance shaders or core ML optimizations tailored for these new ASICs, the system will struggle significantly compared to cloud-based alternatives where specialized hardware handles the load effortlessly. The result of ignoring this constraint is a system that works in theory but fails in practice when deployed on real devices with limited thermal budgets and power envelopes. The friction point becomes most visible when we look at self-hosted services and device-bound applications. Current LLM-powered devices are often limited by hardware constraints that prevent them from running large models efficiently without offloading to the cloud. As Apple pushes its 2027 roadmap, the software stack must shift to utilize these specific ASICs for inference. Failing to do so results in significant performance degradation compared to what is possible with optimized code paths. The break mechanism here is subtle but catastrophic for user experience. A developer might test their application on a high-end desktop GPU and see great benchmarks. Then they deploy it on the new iPad Pro, expecting similar behavior because of raw flops parity in marketing materials. Instead, they find that the model runs at half speed or drains the battery in an hour because the data is being shuffled inefficiently between memory banks instead of staying within the neural engine's optimized pathways. This shift implies a change in how we view hardware specifications as engineering constraints rather than just performance markers. A chip with lower peak flops but superior memory bandwidth and dedicated tensor cores will outperform a generic high-flop GPU for specific generative tasks if it is used correctly. Engineers must learn to design pipelines that minimize data movement between the CPU, RAM, and neural engine rather than maximizing raw compute throughput in isolation. The career relevance of this insight cannot be overstated. Developers who treat hardware as an abstract resource risk building systems that are fundamentally inefficient by 2027 standards. Understanding the shift from a CPU-centric model to one where the NPU is king for inference is becoming a core competency for senior engineers designing local AI applications. The path forward requires proactive refactoring rather than waiting for the new hardware to arrive and then reacting to performance issues. Developers need to start auditing their inference stacks now to identify dependencies on generic GPU kernels or CPU fallbacks that will become performance killers once the 2027 neural engines take precedence for generative workloads. This means looking at how you initialize models, where your data sits in memory during processing, and whether you are utilizing the specific instruction sets designed for Apple Silicon rather than relying on generic PyTorch abstractions that might not map efficiently to the underlying hardware. The goal is to ensure that when these new devices launch, your applications can leverage their full potential without hitting the walls of architectural incompatibility. The future of local AI isn't just about more flops. It's about moving data away from the CPU and onto dedicated neural engines before your battery dies. This transition marks a fundamental change in how we approach system design for machine learning, forcing us to prioritize efficiency and data locality over raw theoretical performance numbers that no longer tell the whole story of what an application can actually achieve on modern hardware. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.